Chapter 10: Mechanical Waves and Sound Wave. Properties of wave. Figure 10.1 shows a periodic sinusoidal waveform. Wavelength or lambda. Definition is the distance between two consecutive particles or points which have the same phase in a wave. Particle B is in phase with particle C, particle P is in phase with particle Q, and particle S is in phase with particle R. The unit is meter. Next, frequency. The definition is number of cycles or wavelength produced in 1 second. The unit is hertz or per second. Period or capital letter T. The definition is the time taken for a particle or point in the wave to complete one cycle. The unit is second. The formula for period is T equals to 1 over F. You need to take note that the period of wave is equal to the period of the particle on wave. Amplitude. The definition is maximum displacement from the equilibrium position to the crest or trough of the wave motion. The unit is meter. Wave number, or K. It is the number of waves per unit path length. The formula for wave number is K equals to 2 pi over lambda. The unit is per meter. Wave speed. The definition is a distance traveled by a wave profile per unit time. The equation is V equals to lambda over T and T equals to 1 over F. Thus, we will get V equals to F lambda. You need to take note the value of wave speed is constant and the unit is meter per second. Particle speed. The equation for particle speed is Vy equals to A omega cos omega t plus V, or V equals to dy over dt. Take note that the velocity of the particle's vibration Vy in wave is varies with time t. It is because the particles execute SHM. The unit is meter per second. Displacement is a distance moved by a particle from its equilibrium position at every point along a wave. The equation is yxt equals to a sine omega t plus minus kx. When the wave propagates to the right, it will have minus sign. When the wave propagates to the left, it will have plus sign. Displacement graphs of the wave is the graph that shows the displacement of all the particles in the wave at any particular time. For example, y equals to a sine omega t minus kx. At time t equals to 0, we will get y equals to negative a sine kx. Then, the graph of displacement y against distance x as shown. Curve C is the displacement of all particles at t equals to 0 second, and curve D is the displacement of all particles at t equals to t1 after the wave propagates by distance x1. Graph of displacement y against distance. The graph shows the displacement of all the particles in the wave at any particular time. For example, y equals to a sine omega t minus kx. For particle at time x equals to 0, we will get y equals to a sine omega t. The graph of displacement y against distance is as shown. Next, for particle at time x equals to 0.25 lambda, when we substitute the value, we will get y equals to a sine omega t minus pi over 2. Thus, the graph of displacement against distance is as shown. Equations for particle in wave y equals to a sine omega t plus minus kx. The particle's differentiation for velocity is Vy equals to dy over dt. The equation will be Vy equals to a omega cos omega t plus minus kx. You need to take note that the velocity of the particle varies with time, but the wave velocity is constant, thus Vy is not equal to V. The differentiation for acceleration will be Ay equals to dvy over dt. The equation is Ay equals to negative a omega square sine omega t plus minus kx. The equation of acceleration also can be written as Ay equals to negative omega squared y. The vibration of the particles in the wave executes SHM.